And so let's go for the next session with Peter.
Yeah. First, some excuse. I messed up some explanation yesterday about lambdas. Actually, you can have as many statements as you want here in the function body. I mixed up the restriction that I was claiming with const expert functions, which I will shortly introduce later, second half of the morning. So in C++ 11, you could do almost everything except C++ 14 added that you could use auto for the lambda parameters and that you could introduce new variables within the capture. Not only refer to variables from the outer scope by saying I want to capture them, but also introducing new variables by saying x equals whatever initial value it should have, would introduce x as a new variable to be used in the capture and to stay alive as long as the lambda is available. So that's our two things I didn't expect.
Those variables that you could declare in a lambda, they will keep their state when lambda executes. So if I say x equals 1, then with each execution I can increment it?
Yeah. Well, these variables are const unless you declare the lambda mutable. If the lambda is mutable, these variables keep their state throughout the lifetime of the lambda object. So when you change it, it will change and stay there unless you forget the lambda. Okay. We've seen yesterday a lot on templates. I introduced you to templates, and this morning I redo a talk I gave a couple of years ago and also last fall on how to use templates to implement design patterns. But design patterns is so much software people stuff. I have a question. Anybody of you have heard of the thing called design patterns? Never heard of design patterns? Okay. In one or two sentences, patterns are about successful engineering stories to actually tell people how to reapply solutions that worked in the past for some problem domain. There is more than just one book on design patterns. I co-authored at least one other book that's quite important on patterns for software architecture, and many people only know the design patterns book. Anybody has read or heard of at least a second design patterns book? That's quite fewer. So design patterns, there's one book by Eric Gamma and some friends of him on design patterns reusing object-oriented design. And I show some of these patterns from that book, which was written well before C++ got templates established, and also before we learned how to use templates effectively, how to apply them with templates at compile time instead of the classical design patterns approach of having variability at runtime. Okay, that's just... So that's what are patterns. So what the classical design patterns book, which is still selling heavily, lacks a little bit is that a good pattern description, in my opinion, not only it's about engineering. Engineering is always about trade-offs. So a good design pattern description would also tell you the trade-offs you have to take if you apply the pattern, and very often that means additional complexity or additional runtime overhead. And with design patterns, it's very easy to introduce flexibility to your code, but it's also very hard to remove that flexibility after the fact. So I've seen people trying to apply design patterns heavily, and then the code was just too hard to actually use or reuse because they had provided too much flexibility. And a lot of Java code around the world suffers from that, too much flexibility and too much indirection, and sometimes you have to take the decision and not introduce just another level of indirection to get more flexibility. And the most important thing is that patterns give us names about concepts of software structure. So if I say the pattern observer, who has some glimpse of what it might mean if I say, okay, I want to have the observer pattern in there. So for example, yesterday we heard a little bit about shared pointer and weak pointer, and weak pointer actually is an observer of shared pointer. So whenever a shared pointer, the last shared pointer gets destroyed, the corresponding weak pointers get notified and reset themselves to the null pointer. So because the original shared pointer or pointed to object is no longer available. That's implemented with the observer pattern. Okay, that's who has seen this book? Who has read this book? Who has heard this book exists? Okay. Just a little bit exercise in the morning. One thing is, in that book there are a lot of C++ examples because that was one of the mainstream object-oriented programming languages at the time. But as from today's perspective, after more than 20 years, it's no longer good code what's in there. Even the C++ code, because it's ancient C++, it uses mechanisms that are no longer applicable. It uses bare pointers, which you are no longer allowed to use after my session yesterday, and you no longer intend to use them. And there are better ways to apply the patterns today. That's where I contributed. We also have some design patterns in there, but it's also for software architecture. One thing that might be applicable to your domain is, for example, what we have in there is pipes and filters, and the pipelining is a typical construct to get parallelization in a code stream that processes stream of data. And what's also, even though it's not described in a way for what you might directly be applied to, but understanding the pipeline is what's described in there, for example. And it exists as for dummies, so you might just get the for dummies version, which is a quicker read. Yeah. So that's a list of the 23 patterns in the design patterns book. Actually, there is one more that's not in the official list. It's called null object, and there's one that I crossed out, and it's spelled Singleton. Anybody of you heard of the Singleton pattern? Anybody of you have applied the Singleton pattern? Get rid of the Singleton pattern. It's almost as bad as global variables, sometimes even worse, because it's a global variable in disguise. And I've consulted companies that had hundreds of singletons in their software and were wondering why they couldn't actually make it work. They could, if you have a singleton in your code, the problem is, one aspect is getting only a single instance of a specific class, which might be a reasonable choice to do, but the other thing is it also provides global access to that single instance, and global access to global data is not a very good thing to provide, especially if you want to have your code unit tested, and also if you want to make it work in a concurrent or parallel domain where accessing global data from everywhere just messes up things or slows things down if you at least protect it with the corresponding mutual exclusion mechanism. I want to take a look at the highlighted ones. It's command, decorator, strategy, and template method. These are, I would say, one beyond observer, some of the most dominant or mostly used patterns. If you look at the description of the command pattern, it actually is about encapsulating some request as an object. And once you have that as an object, you can pass it around. You can parameterize other objects or methods with it, or functions. You might be able to queue things, so you don't have to execute some requests immediately, but might do it later. You might execute it in a separate thread. You might actually log what you're doing, or even support undoable operations by attaching some previous state when you execute the actual request, and provide a mechanism to reestablish the previous state after you want to undo that operation. It even provides a means applying the composite design pattern to establish macros, where you say, okay, I have a collection of these command objects which I can execute in sequence, and I can view that collection of command objects as a single command and execute it as well. Anybody seen that command object? Use the command object after my description right now. Anybody used a function pointer or a function object so far? You all applied the command pattern because you passed a piece of code around as data and later on used that piece of code, that data object, and called out to that piece of code. That's command. Passing some stuff that you can call out around as an argument somewhere. So in C++, we have what we've got in C, function pointers. They usually lack state, but we can overload the call operator, or we can use a Lambda object to actually have instances that are callable like functions. So you have data that we can pass around and call it like a function, and that way we can actually call out to things. We can use std function to keep around these function objects, let's say in a vector of function objects, and call them later, or put them in a queue to call them later, or repeat them, or collect them as a macro, and all things like that. What you won't get with the call operator alone is the feature of undoing things, but that's just one aspect of the command pattern. The underlying principle is that you use, let's say, pieces of code as data, pass them around as arguments, and then call them later on in some other place where you would have written the code instead. Just to give you a very brief, very silly example, we have 3 classes, let's say, of a simple game or whatever, a simulation, a class think, a class walk, and a class hide. Each of these overload the call operator and without taking any parameters. And as I told you, it's bad code. It's just a silly example. And then an execution function do it that takes a function object, std function, and just calls that function. The do it function might also log something. Oh, I'm calling blah, or I'm calling something, or it might do other stuff, but let's just call that. So we can actually use, in this test, in this example code, we can create a think object, pass it to do it, and do it will actually call the call operator of the think object. We create a walk object, call do it with it as an argument, and do it will actually call the walk object. We can directly create a hide object and call it calls its call operator. Here we, just to confuse you, I use hide with the round parentheses to create a default value instead of the curly braces. So here we have curly braces, here we have parentheses, and then we call the call operator on the temporary object we just created. We can even store such a walk object in the function object, call it later on, pass the function object itself to do it, or we can do the same with reassign the function object with a think functor, and then call it again. And it's just silly what would be the output here? Well, I guess it's think, walk, hide, walk, walk, think. Want to see the code running? I hope that is the code I'm showing. Yeah. Now think, walk, hide, walk. Think, walk, hide, walk, walk, think. Yeah. That's what I intended or guessed the output.
Peter?
Yeah.
Performance in this case?
This, sorry. Performance.
Yeah, what, I mean, do we have any function calls or if...
Actually, in that case, using std function gives the slide a performance penalty because it does a thing called type erasure. It will lose the ability of, let's say it will hide the fact what type you actually created and pass it into function object. So using std function is a slight overhead. We could have replaced do it with a template function. Instead of passing a std function object, we would just deduce the type to be passed in, and then there would be no overhead of calling out the function and the call operator.
Will the compiler be able to inline those functions as one of the optimizations?
With std function it won't, but let me change the code to make it the way I just explained, where you don't get any overhead. So instead of having do it with the function argument, we can make do it a template function. And let the compiler deduce the type for us. And come on, why did I do? No, it's okay. This way, you see it still compiles, and now do it will be actually inlined. And now you don't get any, it will also be able to inline these call operators if it would do that, I believe. Yeah. The only case, once you use that std function object, you get a slight overhead because the function object no longer knows the concrete type of walk. It will actually hide the after construction, it will just call out through that API void without any arguments, and will hide the fact that the original object to be called was walk. So you get a level of indirection that is a slight overhead there, and also might use memory to store the object actually.
Yeah, in all the code that I've seen and worked on, especially in the HPC, std function is not really used a lot. Actually, maybe it's used at the top and somewhere where the overhead is not important. But inside, when you do innermost loop stuff, and then you want to pass the function as a template argument. I mean, the function type as a template argument. And so you get in line everything.
Okay, just to show you where it might make sense to use std function, and you might be willing to pay the overhead, is when you construct something like a macro command, and here I'm doing something that is usually not allowed, but I'm doing it anyway. I inherit from a standard library class called vector and put a vector with function objects, and that way it can actually push back or add to the vector any kind of function object that follows this interface without any arguments and returning nothing. And that way I can add a call operator to my macro command class and just execute all the function objects. Here I do, again, the check if the function object is actually valid or not empty, and then I call it. So I won't get undefined behavior if I call a function object that is doesn't have a valid function behind it.
Yep.
The second thing that is a C++11 feature, I use a using declaration for the vectors constructors, and that way I get all the constructors std vector has from my class macro command. And that's quite a convenient feature. Before C++11, you didn't have that flexibility. You would get all the base class member functions, but you wouldn't get the constructors, and you had to re-implement the constructors by delegating to the base class yourself. And that need is no longer there, especially because if you look for a standard library class like vector, it has some interesting tricks to get all the constructor overloads working nicely. And you don't have to care about that if you just want to add a little bit of functionality. Whenever you do something like that, you shouldn't add any data to your classes, because that will can get problematic, and you shouldn't expect to pass macro command as a vector object somewhere else, because it will lose the ability to call out your additional functionality.
Can I add something? There is a Boost library which is called Boost Fusion library, which allows you to declare short vectors of not uniform types. And so you can have up to few tens of objects, and then you can create a fusion vector of actual function types that you can iterate through and get everything in line. The problem is get very hairy. You cannot use a for loop, because the for loop assumes the types are the same. And so you have to do template recursion to iterate through the fusion vectors. And you have somehow, some short sizes. You cannot grow to thousands of functions. But that gives you all the inline stuff. If you really need to do something like this, it's because you have a lot of functions or you are working in a very dynamic setting, I think.
Good. So there is a means to implement something like that without the actual overhead that I introduced here in that example. That's what you're saying.
In certain cases.
In certain
cases.
Okay, we have already seen the macro command, which allows us to use it like a vector of command objects, push back all the things. We can even recurse and push back a copy of our macro command. So calling the macro command would actually call out think, walk, and that's it. And we don't have reference semantics, so it won't get endless recursion. It's just a copy of the macro command as a second, or as the third element in the vector. And if you look at the executable, we see the macro command is actually outputting think, walk, as I promised. Okay, dynamic polymorphism. As I see it, it's the theme in the classic design patterns book and in many object-oriented design texts, where you have a base class defining an interface, or an interface in Java defining how to call a set of subclasses, and clients just use that interface so they can be configured or parameterized with concrete implementations of this interface at runtime. And as an example, there's a strategy design pattern, which is, let's say, the most generic one to understand dynamic polymorphism. Instead of, you delegate some steps of an algorithm to another object, where you define the interface up front, and then different implementations of that object actually will solve the problem for you, maybe with different algorithms or with different preset conditions, and the overall algorithm stays the same on the client side. If you have that problem, you have to pay the overhead of virtual function calls. You have to provide a virtual destructor in the base class if you want to actually allocate these objects on the heap and get rid of them in a safe way. And this calling indirectly over virtual functions is actually an indirection at runtime, and it might, if you do that in a very inner loop, it might cost you a lot, because those virtual functions usually cannot be inlined, because the compiler would not know at compile time which version of the virtual function you're actually calling in a given place. Very often such dynamic exchange is not needed at runtime, but only at compile time. And some people provide variation at compile time using the preprocessor with #ifdef, and I'm sure some of you have seen code like that. It's horrible, it's a maintenance nightmare, and it's easy to, let's say, have one compilation path that wouldn't compile on some platforms, and you only figure out once you try to actually use that compilation path. Why do you want to exchange stuff at compile or at runtime? You might want to have tests where you have a different version of the code to behave differently. You might have different platforms for different optimization strategies. You might have even a different problem size or problem category for the overall same algorithm. Some details are actually different. Just to give you an example how dynamic polymorphism in C++ looks like. Here we have, again, a very silly example. We define a class hello interface where you have a virtual member function to output a message. And because it has a single virtual member function, it has to have a virtual destructor. And you see this code example is pre-C++11. I think so. At least it doesn't use my equals default version of the virtual destructor, which is not a big problem, but I'm not following my own rules. I'm sorry for that. Then we have, let's say, the official implementation to cout, hello cout impl, which overrides the output message virtual member function. We don't have to repeat virtual here because it will automatically be inherited by inheriting from the hello interface publicly. And in that implementation, we actually output hello world to the std cout. And now we have a class that is actually parameterized by a hello interface object. It keeps a reference to that object, getting passed in that reference in the constructor. And it will actually delegate and just, it could have been any kind of name for the member function here. I just happened to use a call operator again because I found it funny when I made up this example to use a call operator as a member function for our hello world object. And it will delegate the actual work to the virtual member functions of the hello interface object that is behind that. You cannot instantiate a hello interface object directly because it has a pure virtual member function that equals 0 up there. That means you cannot actually create such an object. You only can create subclass objects of that hello interface class. In our main program, we just create our hello cout impl object, pass its reference to our hello world object called doit, and if we call doit's member function call operator, it will delegate to our toCout hello interface object to actually call out that. You see, we can actually use polymorphic behavior with stack allocated object. We don't have to rely on the heap as many people think we have to when you do dynamic polymorphism in code. Let's say this is the simulation of the production system. Now, if we want to test things, we learned, okay, we cannot test code that uses cout. But we might want to test our hello world class itself if that is actually working something useful. So what we can do in a test case, we can actually create a hello test impl class that inherits from the hello interface, implement its virtual member functions. Now in a different means, it uses its own string stream object to keep the message that was output around. And for our test case, we use, instead of our hello cout impl, we use the hello test impl, pass that to our hello world object, act on the hello world object, and now we can use our for test hello test impl to figure out what the output actually was. So this means is it allows us to have two versions of the hello world object, one for the real world doing the output and the other one for the test doing the output into a test, into a string stream. If we in C++, instead of using these virtual functions and everything at potentially exchangeable at runtime, we could also use templates and make things exchangeable at compile time. So we no longer need that explicit interface that we used before with the virtual member function. What we now can do is actually we can implement the hello world class as a template class or a class template and pass in the hello interface object that we actually want to use as a type name template parameter, and we actually use the concept that the hello world, the hello interface class actually provides a function, a static member function that will be called output message. We provide an implementation that implements output message using stdcout as before, and in our compile time version of the variation, we have our hello world implementation using the hello cout impl as a template argument instead of a constructor argument. And now if we call out its call operator, it will call out to this hello cout impl output message function. For the test case, we do the similar thing that we did before. We also implement a static member function called output message. It has to have the same name, otherwise it wouldn't be called from this interface here, from this member function here. And in our test case, we just pass in the hello test impl as a template argument and now get for the test the other version of the code called. It's more or less the same mechanism, but just as compile time and not at runtime. The good thing is that this kind of code can be inlined, it can be performed optimal. Even though you have this variability, you wouldn't pay the penalty for any kind of indirection or overhead because everything is resolved at compile time and can be inlined. Where with the virtual function interface, you always pay the penalty of the indirection plus the penalty that it cannot be inlined by the compiler, because when it compiles the hello world class, it will not know which function actually calling, so it will not be able to inline it. Questions? So that's the base case using strategy at compile time with the template parameter. Template parameters are even more curious or interesting. For example, you can have a class that inherits from a template class and passes itself as a template argument. You see, we have here a class curious base that is a template class, and a class curious that actually passes itself as a template argument to its base class, which is a template class. That looks quite interesting, and it's a trick that is used quite heavily, because that way we can use the base, curious base, to add features to the subclass without even knowing the subclass up front. So the base class actually introduces additional features to the subclass, and that's an interesting effect that is quite commonly used in programs employing templates and inheritance. This kind of inheritance typically is not the kind of inheritance you have with virtual member functions in the base class. It's adding features to the subclass through the base class. And I show you one of the features where you can get that. I told you already, don't use Singleton, but there might be situations where you want to actually control the number of instances of a given class. Maybe because you're managing a resource that has only a limited availability, and throughout the program run you wouldn't want more than one or a couple of objects of these resource management objects. And even without global access, you can provide such resource limitation. And whenever I want to create another object of that resource limitation instead of the classical Singleton approach, I will throw from the constructor to avoid instantiate another object of that beyond the number of allowed objects. How can we implement that? This is just an example. For example, we create the class 1 and inherit from a template class limit number of instances, where we pass our own class 1 plus a counter as a template argument, and it will limit the instantiation of class 1 to just one object at a time. So for example, in the test only one, we create one object, the 1, and when we attempt to create another one as a temporary, for example, we assert that it will throw an exception, a logic error, and that actually happens. The test case will run green. So it will, whenever we try to create another one object, it will throw. The same, yeah.
Why passing 1 or 2 as a type and not as a, for example, constructor parameter?
Sorry, I cannot imagine where you want to pass 1 or 2 as a constructor parameter.
For example, if we had an implementation of in the constructor of limit number of instances, and then in the constructor of limit number of instances, we receive a parameter with the number of instances that we want to limit from the...
That would mean that you have to provide your one constructor, or for each constructor of your one class, you have to call out the base class constructor with the right number of, with the same number, 1 or whatever number you want to pass in, and that gives you the problem that you might have to use it several times. the same number, or you might get inconsistencies.
So what you are saying is that it will be error prone.
It is a little bit more error prone, and it requires more runtime infrastructure, especially
It's runtime.
because you cannot actually use the base class itself, because you need kind of a global counter for the objects that you instantiate. That could only be done with a static member, and you have to initialize that static member for all objects. Just passing it to the base class wouldn't work, because you have another instance of your one class passing again one to the base class, and you wouldn't be able to
I see.
merge that with a counter.
Yeah, exactly. Thanks.
So. But I did show you the use case and not how it's implemented, so maybe the other way around, it's more obvious why you cannot do that. So there's just for the completeness, the same thing with the class 2, which would allow 2 instances. And if we have, and we see we can have 2 instances when we try to attempt to create a third one as a temporary, we create a logic, we get an exception, a logic error. But once the lifetime of one of the second one ends here, we are actually free to get another one. It's just we limit ourselves to 2 instances at the same time. And this is how it's done almost. It misses this example, because it wouldn't fit on the slide, misses things like the copy constructor and move constructor to make it right. But the underlying idea is I have a static member variable, so a global variable, per to be limited class. And I use an atomic counter, so any kind of concurrency, even if multiple threads try to create a subclass of limit number of instances more than the allowed numbers, the counter will be right, because multiple threads can actually increase the counter without throwing. And there's another bug in that piece of code. It should be greater equals max number of instances. It's in my implementation, correct, but not on that slide, sorry. I'll just fix it, not to confuse you. So whenever counter is too big, we throw the logic error. Otherwise, everything seems to be fine. We increase the counter. And whenever we one of our subclass objects is destroyed, we reduce the counter. And because the counter is actually parameterized by the class to be limited, we get an individual counter for each subclass that we actually create with the corresponding maximum number of instances. So for our one class, we get a counter that is where the maximum number of instances is 1. For our 2 class, we get a counter, another counter, that where the maximum number of instances is 2. And if we want to have 1,000, we can have thousands of those, and the 1,001st one will just not be able to construct. More clear now? Good. Another pattern that's in the Gang of 4 book, but this doesn't come up in the index, but it's in the text. It's called the null object. When we have something like the strategy class or some other, especially for strategy, you might come up with the default case where you say, okay, that's the regular behavior. The regular behavior very often means just do nothing. And a null object is actually, instead of passing in Java, you could pass, let's say, a null reference, or in C++ a null pointer to say, okay, there's nothing there. That means you always have to check if something is null, and then you do something else. And if it's not null, you call out to that not null object. Instead of having these conditionals, the trick is to provide for the null case a specific implementation, exactly what you put in that if it's null, and delegate just always to the corresponding object and make sure you won't get a null version of that. for our, if we go back to our hello interface, the dynamic version of that, we just can have an implementation where the output message virtual member function does nothing. And if we use that, we still can pass it to as an argument to our hello world object at runtime now, and it will actually do nothing instead of outputting something on the standard output. It's another implementation of our hello interface strategy object. It also works with our compile time static polymorphism, and we can even use it as a default template argument to our hello interface type name parameter. And that way we can actually instantiate the hello world class without providing a template argument, because then the implicit default template argument will be used, and as our implementation says it does nothing, it will do nothing. That's the principle behind the null object. So we can apply the null object with the strategy design pattern as well at compile time as for runtime. And especially if it does nothing, it will actually be inlined by the compiler doing nothing, and if it does nothing, it costs you nothing. That's also something, a trick to provide a parameterization that is optional without paying any overhead at runtime for that feature where you might add something. Mauro, I guess you will use things like that.
Yes, we are using things like that very often. Yes.
Now, template method. Again, that is something I'm sure Mauro or some of the HPC frameworks are actually using. The template method design pattern is about providing a skeleton for an algorithm, so the overall call, and then within the steps of the algorithm, you might call out to primitive operations that are defined later. So like you have overall scaffolding of an algorithm, and some of these steps in the algorithm, you provide the possibility to hook in specific operations, and in the object-oriented world, you would do that at runtime, instead of using the base class, instantiating a subclass of that just provides implementation of these primitive operations in the subclass. And we have the runtime configuration, which concrete subclass you use is the one that actually defines how the overall algorithm works. The problem is, if you do that with virtual member functions, you pay the penalty of the indirect call in the algorithm, and if that happens to be in a very inner loop, you slow down your stuff significantly. And if we look closely, we can actually apply our curiously recurring template parameter pattern and actually have a compile time configuration where we implement the template method as a member function in a base class, which is actually a template class inheriting from its template parameter, and we provide our configuration at compile time as that class template parameter. Just give you a code example for doing that. Let's say we create a class where we inherit from our template parameter, and we have that super duper algorithm where some steps are actually delegated to the superclass, to the template parameter class. It could be done without inheriting, but the inheritance later on, as we see, allows us to actually stack the delegation. We can even do more about that. So what we could do is actually we create an implementation class for these specific steps and instantiate our base class with this template method steps implementation and call out the algorithm. What is the benefit now? because it's a template parameter, the implementations of the step functions could actually be inlined, which couldn't be done with the virtual member function approach, where you would inherit from the class implementing the algorithm and just implement the virtual member function step 1 and step 2. In this case, you just expect the template parameter or template argument to have implemented these 2 step functions and would call out to them.
So currently, without concepts, we cannot check at compile time if this template parameter actually provides the implementation for all those steps.
You will check at compile time. It's only that the compile error might happen here. If you miss step 2, it will happen actually, the compile error will happen here, but it will then say instantiated from here, and then you will know where the problem is. But the problem actually is in the TM impl class. So it's not that you don't get a compile error, you just get a slightly more complicated compile error than it would come with concepts.
Yeah, and anyway, you can implement checks and compile time checks. C++11 provides static asserts. You can put somewhere to check the types, and you can use meta functions to inquiring many things of your stuff. Right? For instance, you can check that a class has a certain function or a certain types, etc. So you can do a lot of stuff before reaching that step, but will make the code look a little bit more complicated. I will show you some examples, but it will give you the error much sooner. So yeah. More work to get more stuff.
But you will get compile errors if it doesn't fit. It's not so that you will get runtime error if some function is missing. Some examples from our unit testing framework, just to give you an overview. If you want to have a look at the source code of the framework, whenever you create a Qt test project, we'll get all the source code. For example, there we have the test class itself. It implements the call operator, and so it's a command object. We have the test runner, which is actually has a run it member function, which is a template method, which calls out to base classes to the listener object passed in as a template argument. And we have the framework provides several listener objects that actually starts out with the null object as a default and has Decorator, so you can stack your own listener if you ever want to have a different, let's say, error reporting from the testing framework, for example. And just to give you an example how that applies, the runner class inherits from its template parameter. The default case is a null listener, and it actually has these 4 different hook functions: start, success, failure, and error. And start takes the test object to print out the test name. The success will actually give a message to the test object, and failure and error combine the test object with a string again for the error message, or with the exception object. The null listener just does nothing, and there are a few more hooks that I didn't show on the previous slide. So we have not only start and success, failure and error, but also begin and end for suite objects. And to show you the Decorator version that is actually applied there, the original Decorator pattern, we have an abstraction as a base class, and a regular implementation of that interface like you would do with the strategy pattern. And there is infrastructure for an object or a group of objects called decorators, which actually implement the base class interface, plus they have a reference to base class object again, And that allows us to, when implemented the interface in the Decorator or Decorator subclass, to add features to the operation and then call out to the base class object that is wrapped. This allows us to dynamically construct wrapper objects around features and add functionality or even hide functionality for an operation. And the classical design patterns Decorator pattern will do that via dynamic polymorphism, and we can exchange that for a statical compilation Decorator. So instead of delegating to our object reference, we delegate to a base class that we actually we delegate to a template parameter with the operation, and that allows us to add additional features to the operation. How does it look at in real code? For example, we have had our listener interface that we use in the runner object, and we can have a counting listener that counts how many successful or failing tests happen to be with counters. It adds a number of counters, initializes them to 0, and then implements these success and failure functions and always delegate to it base class it takes as a template parameter. The default again is a null listener, so we have a termination of the recursion, but we can now add and stack these listener objects around, and that's again the principle of the Decorator, but now at compile time. And if you want to learn more about that, there's a whole book on how to use template parameters for policy-based design and apply all these patterns. Some of the stuff in that book is no longer that complicated as it is presented in that book, because we now have these variadic templates where you can easily have lists of templates, and we have more infrastructure in C++ 11 and 14 and some Boost libraries to do things like type queries, like having things like tuple, which is a standard class now where we can have a list of arbitrary values and write generic code on coping with those elements. But I think that's beyond what I can show you this morning. So there's more to learn. And we are not yet up to break. We still have half an hour, do we? 10:30 was the tour break.
We'll have a meeting at 10:15. So the break at 10:50, so some people can get coffee
and then go. Okay. Don't be afraid of templates. It's just a different means of having a compile time function instead of a runtime function. And instead of using parentheses, use angle brackets to pass things around. And you can pass more than just values. You can pass values, types, and templates. And that's it. For someone with a math background, it's not really a big deal. For someone with just a programming background, it might be a bigger deal, but it's not really that much difference. The good thing is you get this function template argument deduction, so you don't even need to specify all of the template arguments when you use function templates. And because of the overload resolution and the specialization resolution, you can actually do interesting things that is called template metaprogramming. So you program at compile time, and that's interesting. And I don't do the templater demo that I intended to show you because I don't have the plugin installed right now.
So, quick question about templates.
What's that?
So, a quick question about templates.
Go ahead.
So, I'm not afraid of templates, but I'm afraid of the error messages which result from the use of incorrect use of templates. So, are there any tricks to really figure out what's going wrong if you have, 10,000 lines of error messages related to templates?
My recommendation: always look at the first lines, because very often the 10,000 lines, 9,990 of them are actually errors that will go away once you fix the first one. there are tools, and we are trying to do something about that, but I lack, and let's see, I haven't installed the plugin in that instance, and I can just start my slightly older version where I have the plugin installed, which is this one. And let's see.
Well, while Peter search for it, there is an option in GCC, which is -W fatal -errors, that prints only the first error, and I almost always set it on, so I don't have like 50,000 lines of code, just a single error. Even though a single error can be quite long, but the trick there is to learn how to read that error and to take some parsing abilities in your brains at some point. That's it. -W fatal -errors with the S at the end.
Okay, just to give you a glimpse of what we are trying to do, this is my example from yesterday. It just uses the wrong font, I'm not sure why. With the print line template function, variadic template function, with the variable number of arguments with our head and tail version. And what my students implemented, they actually provide a visualization of what the compiler would generate from your code. And if you focus on the main function, it will show us that it will generate a call to the printline function where the deduced template arguments is a character array, an int, and a double. And we have 1, 2 as an int, and 3 as a double. And we can now click on that, and it will drill down and show us the code is actually instantiated. And in the recursion case, it will actually, the remainder is now printline with int and double. And I can drill down again, and it will show us, okay, again, a recursion is, it will print line with a double, and it shows us actually that head is an int. And if we drill down further, we have print line with an empty tail, and that will go us to the recursion base case, where you say, okay, that will never be called because we have that version with the if. And that's my attempt to actually provide help for template programming to see the code that the compiler would instantiate internally, but that you wouldn't see at all unless you create an error message. And it's not as good as I would like it to be now, but that's our goal, to actually provide that information there around that for templates.
So one question, sometimes it's difficult when you have several partial specializations to find which one is actually instantiated. Are you
my goal is
doing
actually
something?
to show that in the templater. Let's see. I have one that is called really hard, and that's mimicking actually the stuff where you have here different versions of allocated traits and alloc traits with different implementations, and it will actually show us that the stack here, stack type is int, and the allocated traits, whatever they are, and it can drill down to whatever they means, and it might actually check some of them. I'm not sure. I should have a version of the example with the actual vector. where we have, if you focus on the main function, there we have a stack with bool, and if we drill down and look for the vector, and I'm not sure if it'll work right now, because, exactly, it won't work because I have the wrong compiler version turned on here. So actually, let me tell you, vector bool, I told you, is a specialization, and it will show you that it will select vector bool in that case where t is bool, and vector, the generic vector, when there's another type here. And it just doesn't work because I have GCC 6, and their vector includes C++ 14 code that our parser doesn't parse yet well. So that's just, if you switch back to a compiler with C++ 03, it will figure out which vector you chose.
Well, that's awesome.
Yeah, but it's not that useful. It should work now everywhere, but it doesn't yet. But that's the idea, to provide you the information which version is selected. And also, well, the ideal would be an interactive debugger for template metaprograms, but there you might get problems when you have very deeply nested templates, and finding them would require too many clicks to get there. But
Well,
we are
it's
working
only-
on that.
yeah, it's only up to 900
So if
clicks.
you have a rich uncle, give us some money and we can intensify our work on that. That's the only limitation right now, that we don't have the manpower, and we still have a lot of ideas, but not always the manpower and time to actually solve them. And while we are at it, you mentioned already, from C++ 11 on, we get much better type queries and type traits, so we can actually, at compile time, the question was, what can we do at compile time when we have template arguments that might not just be the right ones? We can actually change types or query types at compile time, and use static asserts to actually figure out if things are not the way we expect them to be before we get the deeply nested compile errors, which allows us a little bit earlier to actually check at compile time if something went wrong. For example, if you might have got things like compiler warnings of mixing signed and unsigned integer values in a comparison. And if you know that the domain of the values is suitable, you can actually take an integral value and return the corresponding unsigned type with std make unsigned from any kind of t, and this way we can actually call foo with an integer value, and it will give us the corresponding unsigned type as a return type and its default value to that integral type. If it already was an unsigned type, it will just return the same type, and if it was another type, it will an int, it will return the corresponding unsigned int type. That's just the magic that you can do, compute with types and type values, and there are many things to do that's far beyond my abilities to explain today. I've used some of them, and if you're really interested in going down what you can do at compile time with templates, there are libraries. I think the most sophisticated one now, and maybe the most hard to follow its implementation, might be Boost HANA, but there are other Boost libraries that provide type traits and template metaprogramming support that can have very interesting things. The bad thing, or the good thing about Boost HANA, it only works with very advanced C++ 14 compilers. The bad thing, all the other libraries try to be backward compatible and work around the quirks and bad things that the problems some compilers have with templates, especially Microsoft compilers, and that makes the code very hard to understand and read because they provide specific tricks to work around compiler bugs, and that's not code you want to read or write yourself. Any more questions about templates? Now is a chance. to ask. Oh, there's one thing with templates that is on this slide, and it's an abbreviation called SFINAE. SFINAE stands for substitution failure is not an error. And that's one of the tricks that is used heavily in template metaprogramming or in other code, where you actually provide several versions of the same template, or the same template, and use specific conditions to select which one the compiler should actually choose. If you provide several versions of the same template, even if the best match, or if several of these match, where I said with the specializations or the overloads, the compiler might choose, depending on, if one of the matches actually would produce a compile error, it will choose another one. And that's what's called substitution failure, is not an error. Unless you have a perfect match, if that still produces a compile error, you will have a problem. That is then the real problem. Like we had with the equals delete of the destructor, for example, which wouldn't allow you to use a SAC template with pointers. And again, I have some examples of SFINAE tricks in the acute testing framework, but they're easily too complicated to be comprehensible without further digging into it.
Yes, I will, as a suggestion, I would advise people to use SFINAE with enable ifs only, and try to avoid other cases, because they can get quite complicated to follow. So enable if is still considered kind of borderline by many people, like something you shouldn't do, but it's very useful, and that's it. If you are interested, I can show you examples of the use of enable if later.
Just to give you a glimpse, one thing that I use in the unit testing framework, you see these nice messages when I assert equal, it will show you what the expected was as a string and what the real output was. That only works if you have a stream operator overload for your type. If you have a class that implements the equality operator, but not the streaming for the output operator, you have to figure out that your code will not fail to compile in that case, but still produce something useful. And here is some SFINAE code. I'm not sure I can put it big enough on the screen. I say, okay, I want to stream whatever t is, and to actually do that, I have this thing where I say, okay, select built-in shift, and there's a conditional where it says, is output streamable? And I have two versions of select built-in shift class, one where I have a generic bool, and one where I have a specialization where that bool is false. So if the built-in shift is not available, I output, okay, the shift operator is not defined for the type, and give the type ID. If the built-in shift is available, I just call it. If I wouldn't have this selection mechanism, just using the shift operator when it's not available, it would get a compile error. And this trick allows me to get around that compile error by just choosing the right version. And now the trick is, how is output streamable implemented? And that is actually, again, maybe too complicated version. It attempts by blah, 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 looking for, is output streamable impl, which again is a template, and it will actually check if the shift operator application to two temporary values is actually working, and the regular shift operator always return the stream reference, where size of is different from a size of character. And I have a specific version that is returning a character or pretends to return a character. It will never be called because it's just used in this size of version, but it will actually do the overload resolution for that shift operator, where I have a generic one that works every time, And if the non-generic one, where the stream is available version, it will actually provide us with the different size of, and that's tricky magic, and copy paste it and adapt it, and you don't want to invent that yourself.
The phrase tricky magic sums it up quite nicely. Is there anything in the future standards that will make this easier? Because I've been through this process and it's very painful to get right. And once you've got it right, it's great because you can use it and you can cut and paste it and use it in different places. But is there anything in 17 or beyond that will, things like concepts that will make this...
Concepts will make this go away because you will have a concept for that.
Okay.
Even in C++11 and 14, you have a lot of type traits that provide you with a lot of conditionals on things, but I wanted this code to work with C++03. But for example, there you would have, this is output streamable actually will become a concept, and it will actually maybe have an implementation that is less tricky like that, but still needs to look for the shift operator availability. So under the hood, something like that will happen, but it's not that ugly. It will just say, okay, is output streamable, will provide me that I have a type T and a stream type, and the shift operator is available. And if not, the concept will be false and I can do something else. So concepts will make this definitely simpler. And even without concepts, there are a lot of traits like is output streamable that will provide you with the corresponding values in a much simpler way. Like, Mauro, what can we say? Is signed, is unsigned, is something you can query a type.
Is copy constructable, is signed.
Yeah, a lot of traits that allow you, like for example, we had this copy thing in our min function or our vector or suc. Then we can say, or is copy constructible, and then we know that the type actually provides that information. And if it's not copy constructible, we can actually static assert on that and provide a compile error upfront and say, as a message, oh, we require the type to be copy constructible.
In C++11 provides certain facilities for building these kind of things, usually with very few lines of code. For instance, in our library, we have some meta functions to check that a certain function object has a special function with which has set certain kind of arguments, and that in C++03 is super ugly, like I think it's around 50 or 70 lines of code of extremely ugly stuff. And you can write this with C++11 with, I think, 4 lines most.
Okay. Most of this tricky stuff is no longer required with C++11 or 14, and it's even not required at all with C++ with concepts. There's another thing where I have this. For example, if I do equals with integral values, I pass in the corresponding unsigned type to actually convert the value to unsigned before comparing for equality. Equality is not a problem because if the bit pattern matches, the values are okay. And if you happen to have a very negative value and compare it with a very large number that is an unsigned number, bad luck. You might get equality where your intention was not to get equality, but if you write your test case in that way, you get what you deserve. But if you have a return value that's an unsigned, and you compare it, let's say, with 3, which is an int, you don't want to have these warning messages around, especially if you have, let's say, the size of a vector and want to compare that with 3, and this will get rid of that problem. And you don't have to write 3u to get an unsigned value to avoid that warning. Yeah, that's as much as I wanted to show you. And I think we are running out of time. You all want a coffee and the tour. And just to give you a glimpse what I want to do after the break, a little bit on concurrency, not that much, but you can ask me more about that if you want to.